Yeah, good afternoon, every one of you. So in the morning session, we have seen this one, two film theory or two resistance theory. So we have derived these two equations. Okay, there are special cases for this derivations. Okay, these equations can be solved in two special cases. One is if the gas is very much soluble. Then next one is if the gas is very low soluble or sparingly soluble. So then what we can neglect and what we can keep. In what condition the mass transfer coefficient, overall mass transfer coefficient is equal to individual mass transfer coefficient. We will see now. So morning we have derived this equation. Finally, the two final equations, which is relationship between overall mass transfer coefficient in gas phase and individual mass transfer coefficient, and relationship between overall mass transfer coefficient in the liquid phase and individual mass transfer coefficient we have derived. So these two equations will be used in special cases, two special cases that we will see now. So the special case is one thing, case one. Okay, these are special cases. It will be used in problems. Case one is when the gas is highly soluble. Highly soluble. So meaning if the gas is highly soluble, then the resistance to mass transfer, will be in gas phase. Okay, or we can say resistance to the large mass transfer will be in the gas phase. So for example, let us take this equation number 24. From equation 24, 1 by KOG is same thing. 1 by KOG is equal to 1 by kg H by KL. 1 by KOG is equal to 1 by kg plus H by KL. Yeah, H by KL. Now, according to this statement, when the gas is very much highly soluble, if the gas is highly soluble, then the large resistance to mass transfer will be in the gas phase. Means this will be very, very high. This term will be very, very high. Whereas this term will be very, very low compared to this first term. This will be very, very low. Therefore, we can neglect this or put nearly it is equal to 0. Therefore, we can say implies 1 by KOG, which is overall resistance to mass transfer in the gas phase, is equal to 1 by kg, which is individual mass transfer resistance. Under such conditions, we can also reciprocate this one. Therefore, we can say overall gas phase mass transfer coefficient is equal to individual mass transfer coefficient. So either of the case is valid. Okay, when the gas is highly soluble. Then second case is if the gas is case 2. If the gas is very low, or we can say sparingly soluble. Sparingly soluble or very low soluble. Then what happens if this gas is very low means the resistance to mass transfer will not be in this particular gas phase. It will be in liquid phase. Resistance to mass transfer will be in liquid phase. Then the equation 25. Okay, same equation I have provided here. 1 by KOG is equal to 1 by KOG is equal to 1 by HKG plus 1 by KL. 1 by KL. Yeah. Okay. Same equation from equation 25. This one. So according to this statement, if the gas is very low soluble or sparingly soluble, the resistance will be large resistance will be in the liquid phase. Means this term will be very, very, very high compared to this term. So this term will be very, very, very low. So therefore, we can neglect this term gas phase resistance. Therefore, under such conditions, we can say KOG is equal to 1 by KL, or if you reciprocate that equation, then we can say KOG is equal to KL. Okay, these two are valid when the gas is very low soluble. When the gas is very high soluble, these two are valid. Okay, unnecessarily we don't have to waste our time in estimating this term. If you estimate this term, it will be very small fraction that will be nearly equal to 0. For that, we don't have to waste our time. If the statement in the problem is given as if the gas is highly soluble, then immediately blindly we can neglect this term. We can keep this term and this term as equal. If they have given the gas is very low soluble in the problem, directly it has to come up in our mind that this term is negligible. Unnecessarily we don't have to waste our time. Okay, is that clear? Any doubts?
Clear, sir.
Okay, yeah, thank you. Then this one, okay, overall slide I have given this one. This figure is profiles of your gas film, liquid film, and bulk of the gas phase, bulk of the liquid phase. Then major equations, whatever the major equations are there, I have given here major equations, and final equations, this two. And the special cases will be when the gas is highly soluble, this one. When the gas is very low soluble or sparingly soluble, this one is valid. Okay, this slide, everything is contained in that slide. Now we'll solve one problem based on this equations. Yeah, this problem, mass transfer coefficient estimation. Yeah, for a system in which component A, okay, component A is there, is transforming from liquid phase to gas phase. So here if you see in the previous case, it was mass transfer is taking place from gas phase to liquid phase. Okay, for that one we have solved all these equations. Okay, gas to liquid phase, this one. Okay, derivation we have done. But here they are asking liquid phase to gas phase, the mass is getting transformed. Okay, to understand this problem, you have to thoroughly understand the previous derivation. Otherwise, the profile is completely different from the previous profiles. So from liquid to gas, it is getting transformed. The equilibrium is given by Ya star is equal to 0.75 XA. So Henry's law is given, where this 0.75 is nothing but Henry's constant, H, capital H. At one point in the apparatus, the liquid contains 90 mole percentage of A. Okay, 90 mole percentage of component A is there at one location, and gas contains 47 percentage of A, component A. In both the liquid as well as gas, there is certain percentage of solute which is component A. The individual gas film mass transfer coefficient at this point is in the apparatus is this one. So individual mass transfer coefficient means Kg they have given. Gas phase, gas film mass transfer coefficient is Kg is equal to 0.0212716 kilomole per meter square second. Then 70% of the overall resistance to mass transfer. Okay, 70% of the overall resistance to mass transfer is known to be encountered in the gas film. Means 30% is there in the liquid film and 70% is there in the gas film. That's what this statement. Then determine the molar flux of component A, Na we have to determine. Then interfacial concentrations of component A. Interfacial concentrations means Yai, Cai, okay, depending on the given values, Yai we have to determine. Then the overall mass transfer coefficient for liquid and gas phase. So overall mass transfer coefficient is we have to determine KOG and KOL overall. So this is the problem statement. So problem statement is clear. So given data. So what is given data here? So first is let us draw the profile first. Okay, profile is first interface will be there. I am not using different colors. Please make a note of it. So this is interface, and here it is a liquid phase. Okay, previously it was a liquid phase. This is liquid film. Liquid film. Then this is gas film. Okay, this is bulk of the gas and this is bulk of the liquid. We need not to draw that one. Why? Because throughout this profile is same. Then according to the given data, okay, this is liquid phase. This is some other color we will take, gas phase. Gas phase. So what they are saying, the problem is from liquid to gas. Earlier the derivation is gas to liquid, means the concentration profile will be reverse of the previous profile. So how that will be looking reverse? So the 90% mole percentage of component A is in liquid phase. Okay, then 45% mole percentage of component A is the gas phase, means 0.9 mole fraction of A is in liquid phase. So initially it will be started here. Different color I will take. Let us take this one. So this will be constant XA. Okay, previously it was CA, concentrations we have done. Here in the percentages they have given. Okay, instead of going the basis for the percentages, the concentrations, we can take this as a fractions. Why? Because 90 divided by 100 is the fraction. If this is given in mole percentage. So XA is equal to 90 divided by 100, which is 0.9. 0.9 mole fraction of component A is there in the liquid phase. Okay, from that one, and 45% in the gas phase. So YA is equal to 0.45. So mass transfer is taking place from the liquid to gas. So liquid to gas means the profile will be getting like this. Okay, then next like this it will be getting, and from here it will be constant throughout this. This is the YA value throughout this region, and from this region it will be coming from liquid to gas. The mass transfer is from this phase to the previous gas phase. The mass transfer is from liquid phase to gas phase. So you may notice the previous figure also. I'm showing once again that one. So this one, if you see, so gas phase to liquid phase, the mass transfer is taking place. So from here to here, but whereas the profile is liquid phase to gas phase. Okay, you have to make a note of it. Okay, then this is interface. So interfacial concentration of liquid component A in the liquid is XAI, and interfacial concentration of liquid gas component A in the gas phase is YAI. One second. Yeah, then interfacial concentrations of this one. So we can define that one. Henry's law. According to Henry's law, so equilibrium mole fraction of component A in the gas phase is XA star, and this is equilibrium mole fraction of component A in the liquid phase is YA star. So this is there. This we don't have the reading for this one, but Henry's law constant is provided there. That Henry's law, what they have given? Henry's law is YA star is equal to 0.75 XA. YA star is equal to 0.75 XA. So this value 0.75 is nothing but your Henry's law constant, capital H. Then next data is provided, the mass transfer coefficient, the individual mass transfer coefficient in the gas film. So that is Kg. Kg is equal to 0.02716. 2716 kilomole per meter square second. Okay, then 70% of the overall resistance to mass transfer is known to be encountered in the gas film. So 70 percentage. How can we write that 70 percentage? 1 by kg is equal to 0.7 percentage, nothing but 70 divided by 100 into 1 by kog. Okay, in the overall mass transfer coefficient, mass transfer resistance is 70 percentage of this overall mass transfer resistance will be in the only in the gas phase. That statement is this one. So 1 by kog we already have this value. Okay, this value we can substitute from this one. We can find out what is the kog value. So how can we find out the kog value? Kog value is equal to, so this will be coming this side, that is 0.7 into kg is equal to kog is equal to 0.7 into 0.02716. So how much this one? So this is also will get in kilomole per meter square second. You keep your calcs near to you and just try to calculate fast. We have to see the last topic, weighted volt hour. Anybody is having calc or do I need to calculate? Please tell me something. This one is 0.019 kilomole per meter square second. Then next is we have Na is equal to Kog into driving force. Mass transfer coefficient, flux is equal to mass transfer coefficient into driving force. Okay, we can write where is the driving force from liquid phase to gas phase, it is getting transformed. So Ya star to Ya, that is Ya star. By looking at that profile, we can define these equations. Ya star minus Ya. So therefore, we know that Ya star is already 0.75 into Xa. We can find out what is Ya star. Ya star is equal to 0.75 into Xa is we already have 0.9. So 0.7 into 0.9, which will be nearly 0.675. Okay, 0.675 you will get Ya star. So now from this equation we already have Ya, we already have 0.45, Ya star we find out. Therefore we can substitute Na is equal to Kog. We already have this Kog 0.019 into Ya star is equal to 0.675 minus Ya is equal to 0.45 from this figure 0.45. Therefore Na is equal to something you will get in kilomole per meter square second. Okay, yeah, nearly you will get 4.274 into 10 power minus 3 you will get. Okay, this one is first bit. Okay, calculate the flux. Okay, first is A bit, which is the molar flux of component A. Determine molar flux of component A. That is Na is equal to this one. This is the molar flux of component A. Component A. Then B bit is the interfacial concentration of A, means this one YAI, or we can calculate XAI also. Why? Because there is a relationship Ya star is equal to 0.75. Already H value is nothing but 0.75. That we can use for this interfacial concentration also. So let us solve the B bit, which is we already know this one Na. Okay, this is overall mass transfer coefficient. Then for the individual film, we can define this as, so Kg is the individual film mass transfer coefficient. So then from where it is going? From YAI to YA it is coming. So we can say NA is equal to kg into YAI minus YA. So otherwise you can use the fixed law and derive that one. Okay, no problem. Let us do that one also. So NA is equal to JA, we know that one. JA is equal to minus DAB dou CA by dou Z. So for the gases, we know that CA is equal to PA by RT. So therefore we can substitute here CA value. That is, we can say NA is equal to minus DAB dou PA by dou Z. So RT we will take in the denominator, that is DA by RT. Then we can interchange this one. We can transfer this dou Z in the left hand side. So this will be minus DAB DAB RT into dou PA. So now integrate this within the limits. So when you integrate that one, let us say this is mass transfer is taking place from this to this region. So within the film, the origin of mass transfer will take place from higher region to lower region. Higher concentration is this one according to this profile. So this is ZG. From this region to this region it is taking place. When Z is equal to 0, concentration is YAI. When Z is equal to some ZG, concentration is YA. When Z is equal to 0, it is YAI. When Z is equal to some ZG, the concentration is your YA. So therefore, so this is integral derivative cancel. Upper limit minus lower limit, ZG minus 0 is equal to minus DAB by RT into upper limit is, okay, this is PA. Okay, PA also we can convert into PT. Okay, how we can convert into mole fraction? Mole fraction we can convert by just multiply and divide with PT. If you do this one, there is no harm for that one. This PT, we can take it outside the derivative, and PA by PT. We know that YA is equal to partial pressure divided by total pressure. Therefore, we can write DYA, this one, PA by PT is nothing but DYA. Here PT extra will come. So this PT. Then upper limit is YA, lower limit is YAI. In order to compensate for this minus, we can write that NA is equal to DAB PT by RT ZG into YAI minus YA. So we know that flux is equal to mass transfer coefficient into driving force. Here the driving force is this one. So this is flux. And apart from the flux and driving force, whatever the quantity left, that is called as a mass transfer coefficient. Therefore, we can write this equation as NA is equal to K. So this is individual. We can write Kg into YAI minus YA. So by looking at this profile also, just common sense here. So profile means this profile is just changing, like dropping profile, this one. So YAI minus YA will come. Reverse of this one is not possible. Why? Because mass transfer will take place from higher concentration region to high concentration to low concentration region. If you know this statement, by looking at this profile, you can define any equation. So that's what I have defined. We know already NA is equal to flux is equal to mass transfer coefficient into driving force. So driving force, by looking at this profile, so driving force is from higher concentration to lower concentration region. Higher concentration is YAY, lower concentration is YA. We can define like that. Otherwise, you have to solve by this derivation like this. All this procedure you have to adopt. Is that clear? This one, how we are writing this one?
Once again repeat.
Yes.
Once again repeat. Okay, which one?
Equations.
This is shortcut method or this method? Derivation?
Shortcut, sir.
Shortcut. Okay, shortcut is nothing but just see. If mass is transforming from gas phase to liquid phase, okay, this will be liquid film. This will be gas film. So this will be interface, obviously. So when mass is transforming from gas phase to liquid phase means the profile will be, so this will be constant. Why? Because this is bulk of the gas phase. So within the film, according to film theory, within the film mass transfer will take place. Then mass transfer takes place means concentration will be reduced. Why? Because whenever mass is transforming, so some concentration will be reduced or pressure will be reduced. So profile will be just, it will be dropping like this. Concentrations or the pressures will be dropping like this. Then next liquid film. So the gas is transforming into the liquid. So in the liquid, it is also film now. That's why once again the concentrations will be reduced like this. Then finally it will be approached to a constant stagnant value. So if this is a partial pressure for the gases, estimation of concentration in with respect to pressures will be very easy. So this is PA. Then until here it is also PA. Then after that a drop in concentration or pressures will be observed. So this is PAI. Why? Because it is interface. Then here the change in phase is there. This is liquid phase. This is gas phase. So for the liquid phase, concentrations will be expressed as normal, CAI. Then after reaching here, it will be Ca. And throughout this bulk of the liquid phase, it is Ca. Once again, Ca. Here also PA. From within the film volume, mass transfer will take place. By looking at this one, for example, if you want to find out how much flux is for this mass transfer within the gas film, you can write like this. Na is equal to, if you know this one, flux is equal to mass transfer, product of mass transfer coefficient into driving force. So driving force, we know that one. Pressure difference or concentration difference is nothing but driving force. Here flux, Na is flux. Mass transfer coefficient, let us, for example, you are operating, you are just checking within this gas film, what is the mass transfer coefficient, what is the flux, okay, how the mass transfer is taking place. How you can write, this is dropping. We know the statement that mass transfer will take place from higher concentration region or higher pressure region to lower pressure region. Okay, higher concentration to lower concentration or lower concentration to higher concentration. According to this graph, when this graph is dropping like this, what is the higher concentration? PAI is the higher pressure or PA is higher pressure? Can anybody say? What is the higher pressure by looking at this graph?
PAI.
PAI is the higher. This is dropping, see. If you put a scale here, okay, scale C, if you put a scale here, 0, 1, 2, 3, 4. 3 is greater or here PAI is here. Means it is around 1.6 or 1.7 it will come. 3 is higher or 1.7 is higher?
3 is higher.
3 is higher. Obviously, by looking at this profile, we can define that this is higher pressure and this is lower pressure. So you have to just write, since this is, we are writing for the gas film, individual film, we have to write mass transfer coefficient as kg into higher concentration to lower concentration. Driving force is from PA minus PAI. For example, if you want to write for this one, this film, then this is also flux is equal to mass transfer coefficient for the liquid phase. It is coming as a liquid. It is individual only. For only one film we are concentrating. Then we have to write it is liquid KL. Then what is bigger here? CAI is bigger or CA is bigger? It is bigger
CAI.
and this is bigger. CAI is bigger. So directly we can write CAI minus CA. And if you want to write overall to this one, okay, overall two films, gas film also you have to write, liquid film also you have to write, then you have to use the same thing. Flux is equal to mass transfer coefficient into driving force. The overall driving force is here. So here equilibrium concentration for the liquid phase is Ca star. And here equilibrium pressure for the liquid phase is Pa star. So if you want to write for the gas terminology, you have to use pressures. If you want to write for the liquid terminology, you have to use concentrations. So mass transfer coefficient for the overall two films, gas film also as well as liquid film also. Then you have to write this is OG. This is mass transfer coefficient overall mass transfer coefficient with respect to gas phase. So mass transfer coefficient you have fixed. Now the driving force you have to look throughout this graph, whole graph, not only individual film. In this case, we have seen only this one. In this case, we have seen only this one. Now this is overall, no? That's why two films also we have to look. So driving force is from PA to PA star. Which one is greater? PA is greater or PA star is greater? Which one is higher value? See, here see, this is PA is located here, but PA star is located here. So which one is higher? PA is higher. Just immediately you can say, tell PA minus PA star. Okay, same overall mass transfer coefficient for the liquid phase also you have to do. So that is KOL, overall mass transfer coefficient in the liquid phase. Now concentration terminology. Since this is liquid, concentration you have to use. So concentration means here Ca star to Ca. Which one is higher? Higher value Ca star or Ca? Ca is here. Ca star is higher. So we can write that this is driving force is from Ca star to Ca. How we are writing the bigger value to lower value means mass transfer will takes place from MT. Mass transfer will takes place from higher concentration region to lower concentration region, or we can say higher pressure to lower pressure. If you know this statement, mass transfer, how it is taking place from higher concentration to lower concentration, and also flux is nothing but a product of mass transfer coefficient into driving force. You can write this one by looking at this graph. Okay, this is for gas film, for the mass transfer from gas to liquid, but our problem is from liquid to gas phase. Reverse direction it is taking place. Now can we define this for our region? So once again I will draw this one. Okay, we need not to draw once again. Just try to write here only as a separate plane. So see, if you put a scale here, so throughout this one, the same scale is applicable for every line which is there here. If this you fix 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, now see. Okay, XA is a bigger value. Then next coming is a YA and XAI. Okay, same, almost same value. Okay, same region it is having. Then next small value compared to these two values is YA. Okay, throughout this YA only, throughout this XA only. Now we can define NA is equal to flux is equal to mass transfer coefficient into driving force. We know this one. Flux is equal to mass transfer coefficient into driving force, that is DF. So flux is equal to, if you want to calculate for this film, liquid film, now what you have to write? K, mass transfer coefficient. Since this is in liquid phase, that too only one film we are taking, that is KL, individual mass transfer coefficient. Driving force. What is the driving force here? So higher concentration region to lower concentration region, mass transfer will take place. For the liquid film we are thinking. For the liquids only, mole fractions is denoted by XA. For the gases, mole fractions are denoted by Ys. We know this one. So higher concentration is XA. So that is XA minus only one film we are concentrating. So this will go until XAI. XAI is smaller. XA minus XAI. If you want to write for this gas film, how you can write? Na is equal to K. So this is gas film. So we have to write one film only you are thinking about. So we have to write not O. O means overall. Throughout two films also you are simultaneously operating. But here only one film we are concentrating. So Kg into higher concentration region. So higher concentration is YAI, and in the gas phase lower concentration is YA. So this is YAI minus YA. If you want to write for the overall, okay, 2 films also you have to write. Then this is also same. Na is equal to mass transfer coefficient is denoted by K, and overall 2 films you are referring. Then you have to write overall. O means overall. So gas terms you have to write. Then G you have to denote. Then mass transfer coefficient is already there. Then driving force you have to fix. So what is the driving force for this one? So this one is driving force is from liquid to gas, it is coming from liquid to gas, reverse direction. So in this region, the overall driving force is from Ya star. So this is gas. For the gases, mole fractions are denoted by Y. Means Ya star is a bigger value minus smaller value is Ya. So this is Ya star minus Y. In terms of liquid terminology, if you want to write means Na is equal to overall. So this is KO liquid, overall gas phase, liquid phase mass transfer coefficient into now gas phase driving force is XA is bigger value. Then XA star is a
XA
smaller
minus
value.
XA star.
Yes, exactly. XA minus XA star. So like this you can write by looking at these profiles. Okay, if you understand this profile, it is very, very easy. Draw this profile in problem, then only it is easy. Otherwise, you have to go for that particular derivation. This derivation entirely you have to derive. That is unnecessarily waste of time. So instead of wasting our time in defining such a conditions, we can directly by looking at these profiles, we can do this one. Is that clear?
Yes, sir.
Yeah. Then continued with our problem. Just wait 1 second. This is not operating. Okay, let us solve. Part B is B bit is yeah. Then part B is continued with a problem. Until here, it is explanation only. Okay, all this is the explanations. Okay, part B is according to our problem. The interfacial determine the interfacial concentration of A means YAI you have to determine. So how to determine that one? We already know Na is equal to kg into, so driving force once again we can define. So how the driving force is there here? From YAI to YA driving force is there. That is yeah, from YAI to YA the driving force is there. So in this one we already know what is flux we have calculated here in the first bit, which is 4.274 into 10 power minus 3. 4.274 into 10 power minus 3 from the A bit is equal to kg also we already have. Okay, kg is equal to, they have already provided 0.02716. That is 0.02716 into YAI we don't know, minus YA also we have. That is some 0.45 or something. Yeah, 0.45. 0.45. Therefore, we can calculate this one. YAI is equal to 4.274 into 10 power minus 3 divided by 0.02716. So it will be coming plus 0.45. Okay, therefore YAI is equal to something you'll get. How much it is? Yeah, this is 0.607. 607. Then next one is C-bit. Determine the overall mass transfer coefficient for liquid and gas phase. KOG and KOL we have to determine. So already KOG we have find out here from the given data itself. So KOL we have to find out. So this one we have find out YAI, and this is C bit, which is KOG is equal to what and KOL is equal to what they are asking. We already know KOG from the given data itself is KOG is equal to 0.019. 0.019 kilomole per meter square second. Now we have to determine what is KOL. So let us use the formula, the relationship between the two individual mass transfer coefficient and final mass transfer coefficient, overall mass transfer coefficient. Let us use this equation, equation 24. 1 by KOG is equal to 1 by kg plus h by kl. From yeah, then we can use, we know that relationship between overall mass transfer coefficient and individual mass transfer coefficient is 1 by KOG is equal to 1 by kg plus h by kl. We know this one. Now everything data is there. KOG is already here. So that is 1 by implies KOG is 0.019 is equal to 1 by kg they have already provided. Okay, kg is this one 0.02716. 0.02716 plus h is also they have given 0.75 I suppose. Okay, from the relationship between that fraction, this one 0.75, h is equal to 0.75. That is, this is 0.75 divided by KL. So from this we can easily find out what is KL. So that is 1 by 0.019 minus 1 by 0.02716 is equal to 0.75 by KL. Therefore, we can write KL is equal to 0.75 divided by 1 by 0.019 minus 1 by 0.02716. So this will, you will get the answer. Yeah, you will get nearly, this is KL is equal to 0.0143 kilomole per meter square second. This is individual KOG, okay. KL, okay, this is individual mass transfer coefficient. Among this formula, this is individual mass transfer coefficient we have find out. Now we know the second formula from equation, relationship between the two diffusivity, other formula, which is, we know that 1 by KOL is equal to, this formula is 1 by KOL is equal to 1 by H kg plus 1 by KL. This is second liquid phase, we have derived that one. So this one, 1 by KOL is equal to 1 by H kg plus 1 by KL from equation 25. Then from that one, we can calculate overall gas liquid phase mass transfer coefficient, KOL. Okay, this is 1 by KOL is equal to 1 by H is 0.75, kg is here, this is kg 0.02716 plus 1 by KL is just now we find out, that is 0.143. Therefore, we can find out this one, KOL is equal to 1 by 0.75 into 0.02716 plus 1 by 0.143. You can find out that one. Overall liquid phase mass transfer coefficient is equal to, so this will also have units kg, kilomole per meter square second. Okay. This is wrong, I think. Yeah. This is KL is equal to, nearly you are getting 0.0477. Okay, this is 0.0477. Okay, nobody is calculating, I think. That's why you didn't notify this one. 0.0477. This is 0.0477 and this is also 0.0477. 0.0477. Then finally you will get this one in the bracket. Yeah, this one you will get 0.142 kilomole per meter square second. Okay, I hope it is clear. Any doubts here until now?
Clear, sir.
Yes.
Okay, then I hope no doubts further for everybody. Okay, only 2-3 people are responding. Okay, in the same thing in the slides, everything is given. Just go through this slide. Whatever the major equations are there, that I have kept here. And in the next class, we are going to see the mass transfer coefficient estimation using wetted wall tower. Mass transfer coefficient using wetted wall tower, we are going to see. Okay, before coming to the next class, we just see the slides once again and what are these formulas, everything is given in the notebook. Just try to revise and come. Okay, preview and then come. We will try to solve this one. And finally, this is the completion of unit. Based on this equations, we will try to solve 1 or 2 problems. Then we will conclude this unit. Okay, any doubts, anybody?